Greetings everyone. So my presentation topic is revenue model learning of slice broker in the presence of Byzantine faults. So I am Muhidul Islam Khan. So I'm presenting this topic. And basically, if we look at the topic, then we can see there are three important keywords here. One is revenue model learning, another one is slice broker, and the last one is presence of Byzantine faults. So basically we will try to learn a revenue model for a slice broker, and there will be some Byzantine faults which we will try to detect, and uh, we will learn the overall revenue model for the slice broker. So if we look at the overview of this presentation, so at first there will be some background, then there will be some objectives, then I will define the problem, then there will be a proposed method, then I will discuss the results, I will give some discussion, and finally I will conclude this presentation. Now the background. So as I told that there are three keywords: revenue model learning, slice broker, and also the Byzantine fault. So we can see that this slice broker can be a very important entity in future 5G, or we know that multi-access edge computing, or MEC, and network slicing, these two are very important technologies for the fifth generation cellular network. And how does MEC help us? MEC basically will help to reduce the latency, offload the cloud, and allow context awareness. And basically it will distribute the cloud system in a way that the latency will be reduced. Now, network slicing basically allows to create heterogeneous services on top of shared infrastructures. Now, in this scenario, slice broker comes, and slice broker will basically play the intermediary roles, who will buy the resources from the infrastructure provider, who will make the slice and will sell to the tenants. So here this figure comes. If we look at this figure, we can see that the slice broker in the middle. So there are communication between infrastructure provider and also with some tenants. So the tenants can give some demands for these slices, and the slice broker will buy the resources from the infrastructure provider and will make the slices for the tenants and will sell to the tenants. So it's very important to think about the profit for the slice broker. Now, um, as we know that it will be distributed, so and in this real world right now, billions of devices will be connected in future. So there will be some hackers, there will be some nodes or devices which will provide misleading information or misinformation about the resources, and which can be very harmful for the profit making for the slice brokers. So we will basically try to learn the revenue model in the with the presence of some faults. Basically, we will consider the Byzantine faults, and let's see that how it will work. So, our objectives. So we will consider the presence of Byzantine faults. Basically, they send the inaccurate information about service availability and resource consumption, and also they can make miscalculations about any decisions. So those are really harmful. So in order to solve that problem, we basically will consider or propose a method based on a multi-agent environment. We will see later that it will be based on federated learning or federated architecture, and we also consider cumulative gradient elimination, or CGE method, um, for this revenue model learning, and we will try to maximize the revenue. And finally, we will evaluate the effectiveness of the proposed solution by comparing it with some reference solutions. So how we can define the problem? I think this figure will have all the answers, how the problem is defined. So as I told, that our method is based on federated learning or federated architecture. And on that, we also used some gradient elimination method. So that will really be helpful um, for detecting Byzantine faults. Now, how 5G MEC structure can be suited with this problem? So we can see that there are some MEOs. So this MEO is basically the multi-access edge orchestrator, and under this orchestrator there are some MEH, which are multi-access edge host. Together each cluster basically is forming a MEC system. So MEH, we can see that in MEH there are some chunks of resources, and also the slices S1, S2, S3, these. So they can provide the resources, and MEO can also set the price like C1T, C2T, C3T, and these are combining, and also the final price PT is generating. And also we can see some demand is generating from the slice tenant. They are putting demand for the resources. And in our proposed method, we consider this demand model will be changing based on the set prices. So it's very important, like when the price like real world, when the price is increased, the demand will be decreased, and when the price is decreased, the demand will be increased. So in this way we set this demand. And then there is a role for server as well. So server is collecting basically the gradients, which will be calculated by the MEOs. And these gradients, after getting the gradients, server also set up calculate the weight, and the server sends the updated weight to the MEOs, and the server resides in a slice broker. So this is very interesting, and hopefully this will be very revolutionary in the field of 5G MEC. And now let's see that how the demand or requirement works. So this is basically the demand function. Um, so updated demand will be basically based on the prices at time step t, and also time step t minus 1. There will be a shocking function. This shocking function is basically controls the changes, or basically it will provide the dynamic properties to the demand function. When, as I told, when the price will be increased, the demand will be decreased, and when the price is decreased, the demand will be increased. So this shocking function is very important. And also we can see that the positive changes will be calculated by this way, and the negative changes of the prices will be calculated by this way. So this is our demand or requirement function. Then the overall objective function is to maximize the revenue, so which is just the multiplication of the price of the resources and the allocated resources. So we will try to maximize this price of allocated resources and amount of resources to be allocated. Our goal is to maximize this revenue, and there should be some constraints, like our demand should be fulfilled, so it should be less than or equal to capacity of the resources. And also it should fulfill the overall demand. So there are two constraints based on capacity of the resources and demand of the resources. Now the presence of Byzantine faults. So we will have a set of data. Basically MEO has this set of data, and this data set are this ZM1, ZM2, and the others. This data set is basically consist of the revenues, calculated revenues, and that I showed in the previous page, that how we calculate the revenue. And so now there will be some also some faulty data, like FMT. So for each agent at each time interval, the actual collection of data points can be two types, like ZMT and FMT. So ZMT is when agent is non-faulty, and FMT is basically when the agent is faulty. Now we will consider two types of Byzantine faults. One is gradient reverse, and another was a level flipping. Why we consider only two types of Byzantine faults? Because these two provide a good impact in the system, and these are very harmful for taking decision or for learning any model. So gradient reverse faults provide a significant impact on resource allocation because it causes the misallocation of resources. And it also acts as a Byzantine fault where nodes in the network behave in an unpredictable manner. And here we consider the gradient reverse faulty agent sends the server a vector directly opposite to its correct stochastic gradients. So it will basically send the just opposite values of the gradients, and this can be really harmful for to decide about the allocation or to decide about the revenue model learning. Now, level flipping fault, there is another type of fault. Uh, Basically, it nodes in the network intentionally flip the training data's mod label, and also it can be harmful because it creates incorrect model predictions. And so and it can mislead the system, and it can be very harmful for learning any types of model or revenue model. Now, how our proposed algorithm works, as I told, that our proposed algorithm is based on a federated learning or federated architecture, and also we use cumulative gradient elimination. Now, how the steps will be, how the whole system is working. So for each time interval, if we divide by some steps, then the first step, MEOs basically calculate the stochastic gradients with k data points with the initial estimate of the weight. So there will be some initial estimation of the weights. So basically by this equation, they will do this calculation. Then step 2, MEO send the calculated gradient to the server of the slice broker. Then the server sort out the received gradients for eliminating the largest Euclidean norms. So we will this is very important step for us in our algorithm, because now we will eliminate some gradients based on cumulative gradient elimination or CGE method. We will calculate the Euclidean norms, and we basically will skip those gradients who has the largest Euclidean norms. So this will be very helpful to ignore the Byzantine faulty nodes, because even if they send some odd values, then by calculating these Euclidean norms or gradients, then we will basically can skip the highest deviated values. So those noisy values can be skipped by this way. This is very important for us. Then the server update the weight with the remaining n minus e gradients. So it will be calculated in this way. And then the server of the slice broker basically broadcast the estimate of weight to all MEOs. Each non-faulty agent I sends to the server a stochastic gradient of the global expected loss function, which is basically QMW. So this is also important to share. So if these steps are continuing, then the whole system works like this way, and we can easily detect those Byzantine faulty nodes. Now, if we come to the results, that we basically calculated the loss function over the epoch, and we can see that there are very good results considering no Byzantine fault. If we consider one Byzantine faults, then we can see the loss is a bit higher at the beginning, and then we can see two Byzantine faults, we can see loss is very much high. But over the time period, we can see that the loss is decreasing. It's for our learning algorithm. So this is very important, that even with the two Byzantine faults, we can see the loss is decreasing over the time period or over the epochs. So our system is working very nicely here. Then if we consider the revenue with two faulty nodes, one faulty nodes, and with no faults, we can see that with no faults, as usual, the learning algorithm works very fine, and it's the revenue is maximizing, initiating with the 4,000, and with the one faulty node, we can see that there are some increasing trends, and then we can see there is a downfall after the epoch number 5, and this is basically for the faulty nodes, and we can see that it's overcoming the situation, and it's learning the proper revenue model, and it's increasing trend again. So our learning algorithm is working. And also with the two faulty nodes, we can see that it provides the least revenues, and it's always at the lower side comparing with other two. So this is very interesting. And if we compare our proposed method without CGE, then also we got some interesting results, because we wanted to compare that without CGE how it's working, because CGE is not a very common thing for the federated learning. So that's why we used CGE. We needed to show that as well, and we got some interesting results here. So you can see that revenue without CGE, there are very higher amount of revenues at first, but it goes very rapidly down, which is not good. But our revenue with proposed method, here we also consider two Byzantine faults. So we can see that with two Byzantine faults, even with two Byzantine faults, it's working really nicely, and it can. There are some downfalls, but at the end, it's increasing, and it's avoiding those Byzantine faulty nodes. So, and this is very important, because we can prove that now that CGE is very important in our scenario. And now we also consider it with a distributed learning, like normal Q learning. This is also important to compare, because I think most of the existing works use Q learning for learning. So here we can see that revenue with distributed learning, considering two Byzantine faulty nodes, initially it's very higher, but we can see over the time period it's rapidly going down, and it's getting saturated, and it's getting down comparing with our proposed methods. So it's providing a gap after 17 epochs or 18 epochs. So, and with our proposed method, we can see that the revenue is behaving, even with the two Byzantine faults, behaving nicely. There are some downfalls, but it increased at a time period, and it overcomes the situation of the faulty nodes, and it's learning the revenue model nicely. So this is really important. And finally, we can see that we can observe that with no Byzantine faults, the amount of loss is significantly less. But on the other hand, the loss also increases with the increase of Byzantine faults. So it's very natural phenomena. Then we can observe that the revenue is increased over the epochs with no Byzantine faults. We can observe that we can get the lowest revenue for the maximum faulty nodes. or faulty agents. And our proposed method outperforms the distributed learning algorithm or normal queue algorithm. So this is what we found. Then finally, we can see that we can say that in a dynamic scenario, the slice broker basically needs to learn the revenue model to decide the price, slice price that maximizes its revenue. The slice broker needs to take into account the presence of Byzantine faults that aim to compromise the decision process. So it's very important to take care about these faulty nodes. And in this context, our multi-agent environment implements cumulative gradient elimination in a federated architecture in order to maximize the revenue while considering the presence of Byzantine nodes. So it's and this work is very noble because there are no existing works which considers these Byzantine faulty nodes to learn any types of revenue model or to learn about the profit model. And our evaluation highlights the economical benefit of using our algorithm. So this is really great in our case. So these are the things that I wanted to share in this presentation. And thank you for your attention. Thank you so much.